Welcome to Module 6. Today, we are embarking on a critical journey through the diverse landscape of food production. Our topic is Agri-Systems across the urban-rural gradient. As the title suggests, we are going to explore a spectrum of climate-smart food systems, ranging from the high-tech rooftop gardens of a dense metropolis to the sprawling industrial orchards of the open countryside. I want you to start by challenging your assumptions with a simple question. Does a tomato grown on a balcony in Los Angeles have the same environmental footprint as one grown in a massive field in the Central Valley? To the eye and tongue, they may seem identical, but the invisible systems that produce them, the water sources, the energy inputs, the labor models, and the food miles traveled are radically different. Today, we are going to unpack those hidden differences to understand a fundamental truth: how physical space shapes sustainability. Our roadmap for this session tracks the journey of food from the city center to the rural edge, divided into three focused lessons. We will begin with Lesson A, From Balcony to Back 40, where we go beyond simple definitions. We will analyze the urban-rural gradient to understand the economic engines, specifically the inverse relationship between land cost and food miles, that dictate exactly where we grow our food. Next, we move to Lesson B, Climate-Smart Growing Spaces. Here, we shift from geography to engineering. We will explore how distinct environments demand distinct resilience strategies, comparing high-tech urban vertical farms with compost-heated Peri-Urban greenhouses. Finally, we conclude with Lesson C, Tech and Metrics That Matter. This is where we strip away the marketing buzzwords and look at the hard data. You will learn to calculate water use efficiency and energy use efficiency, equipping you with the math to distinguish between genuine sustainability and mere greenwashing. By the end of this hour, you won't just look at a farm, you'll look at a system. Let's officially launch Lesson A, From Balcony to Back 40. For those unfamiliar with the idiom, the Back 40 refers to those remote, often unvisited acres at the far edge of a massive farm, the middle of nowhere. In stark contrast, the balcony is right here, woven into the dense fabric of the city. The core question driving this lesson is simple but profound. How is physical space reshaping where and how we grow our food? Look closely at the images on the slide. On one side, you see vertical hydroponic towers tightly squeezed into repurposed shipping containers, a marvel of high-density engineering. On the other hand, you see GPS-guided tractors roaming vast, open fields. These aren't just artistic choices. They are specific adaptations to the unique pressures of their environments, one fighting for space, the other fighting for scale. So, why does this gradient matter? It is not just an academic concept. It is a critical issue of human geography. Currently, over 55% of the global population resides in cities, and that figure continues to climb every single day. As these urban centers expand, they have a nasty habit of paving over the prime farmland that historically fed them, pushing agriculture further and further away. This reality makes the peri-urban zone, that transition area between the suburbs and the true countryside, absolutely vital for our fresh food supply. It is the battleground where housing and farming compete. Furthermore, understanding this gradient allows us to optimize for food miles. It is inefficient to truck heavy, perishable items like lettuce or tomatoes across the continent. If we can design systems where these nutrient-dense foods are grown in the urban or peri-urban zones, closer to the consumer, we can drastically reduce the carbon footprint associated with transport. To understand our food system, we must define the three distinct zones of the urban-rural gradient. First, we have urban agriculture in the densely populated core. Because land here is scarce and expensive, these operations are microfarms, utilizing rooftops, basements, and shared spaces. Farmers here often work with short-term contracts and must intensify production to make these small, non-agricultural spaces viable. Moving outward, we enter the peri-urban zone, usually called the urban fringe. This is a dynamic transition area where residential housing and farming mix. It serves as a middle ground that hosts nurseries and greenhouses, benefiting from land that is cheaper than the city but still close enough to local markets to reduce travel time. Finally, we reach rural agriculture in the sparsely populated countryside. Here, the strategy shifts to extensification, spreading out over massive, consolidated parcels of land. While this zone maximizes production volume through industrial scale, it faces the challenge of being the farthest from consumers and relies heavily on long-distance transport networks. Let's look at the economic engine behind these zones' differences. This chart shows an inverse relationship, which is a fancy way of saying that when one thing goes up, the other goes down. On the left, look at the urban zone. See that huge orange bar? That is the price of land. It is super expensive because farmers here have to compete with high-rise apartments and businesses for space. But look at the red bar for food miles. It is tiny. That is the trade-off. You pay a lot for land, but your customers are right next door. Now, look at the rural zone on the right. It flips the script. The orange bar for land cost drops way down because land is cheap and plentiful out in the country. But the red bar shoots up. That is the distance tax. You save money on land, but you have to burn a lot of gas trucking that food hundreds of miles to the city. In the middle is the Peri-Urban zone, the Goldilocks spot. It balances reasonable land costs with a reasonable travel distance. This graph teaches us a simple design rule. You either pay extra for the land to be close, or you pay extra for the transport to travel far. Space doesn't just dictate cost. It fundamentally dictates who does the work and how they are paid. In urban agriculture, the labor force is unique, often composed of volunteers, community activists, or students like yourselves. The wage here isn't always monetary. It's often civic engagement, education, or access to fresh food. However, this reliance on unpaid labor raises questions about long-term financial sustainability. Can a farm survive if it relies on goodwill alone? In the peri-urban zone, we see a shift to a hybrid model. These operations, sitting on the city's edge, often employ small, hired crews or rely on family labor to manage greenhouses and nurseries. It is a middle ground, more commercial than a community garden, but lacking the industrial scale of the rural sector. Finally, out in the rural zone, the model shifts entirely to seasonal and migrant labor. These massive monocultures depend on a workforce that travels for the harvest. But this is changing rapidly. As labor becomes scarcer and more expensive, rural farms are aggressively adopting automation, replacing human pickers with robotic harvesters and GPS-guided machinery to keep the food supply chain moving. Let's ground this in our own backyard. California. First, zoom into the urban zone of downtown Los Angeles or San Francisco. Here, farming is an engineering challenge. You'll see rooftop gardens utilizing high-tech lightweight soil mixes because a standard roof cannot support the weight of heavy field dirt. These projects are vital not just for food, but for building community resilience in dense neighborhoods. Move out to the peri-urban edge, like the greenhouse belts of Ventura County or the margins of the Salinas Valley. This is where the pavement ends and production begins. It's a high-stakes buffer zone where growers compete for land with housing developers, yet it remains critical for supplying our fresh berries and leafy greens to local markets. Finally, drive out to the rural heartland, the Central and Imperial Valleys. This is industrial-scale agriculture at its most massive. We're talking about miles of almond and citrus orchards that rely on complex aqueduct systems to turn a semi-arid landscape into a global breadbasket. It is a completely different world from the city rooftop, yet both are essential pieces of the same puzzle. So how do we actually plan for all this diversity? We borrow a powerful tool from the new urbanism movement called the transect. Think of the transect as an ecological cross-section. Just as a biologist might study how a wetland transitions into a forest, urban planners use this to slice the human habitat into 6 distinct zones, ranging from T1, which is pure, untouched wilderness, all the way to T6, the dense urban core. Why does this matter for food? Because it gives us a vocabulary for placement. You wouldn't put a 500-acre tractor farm in a T6 urban core. It doesn't fit the habitat. And you wouldn't put a vertical skyscraper farm in a T2 rural reserve. To operationalize this, we use the SMART code. This is a model unified development ordinance that acts as the operating system for the transect. Unlike traditional zoning that separates uses, the SMART code uses form-based codes to regulate the physical form of the built environment. This ensures that our food systems, whether community gardens or massive orchards, are designed to fit the specific zone where they naturally belong and function best. Let's look at some specific technologies in the urban zone. The defining characteristic here is using found space, locations never intended for farming. We aren't clearing land. We are adapting infrastructure. First, look at the rooftop kale beds. In dense cities like San Francisco, we utilize empty commercial roofs and modular planters. However, you can't just dump ordinary soil up there. Wet soil is incredibly heavy and could collapse the roof. To solve this, engineers must first verify structural load limits and install safety railings. Farmers then use specialized lightweight planting mixes and precise drip irrigation to keep the weight manageable, allowing them to grow high-value crops right above where they are consumed. Next, we have shipping container farms. These are standard 40-foot insulated steel boxes retrofitted with vertical hydroponic racks. They are plug-and-play systems that allow us to grow food anywhere, even a concrete lot, year-round. But there's a massive trade-off. We replace free sunlight with LED grow lights that run 18 hours a day. This creates a system with very high energy costs but incredible reliability and control. Consider microfarms in school parking lots. We can't dig into the asphalt, so we build up using wicking beds. These planters feature a water reservoir at the bottom that draws moisture upward to the roots via capillary action, drastically reducing watering needs. By filling them with compost made from cafeteria waste, schools create a closed-loop system that turns dead pavement into a living classroom. Let's move outward to the urban fringe, roughly 10 to 20 kilometers from the city center, where we encounter Peri-Urban greenhouse belts. This zone acts as a vital buffer between the concrete of the city and the open fields of the countryside. Here, farmers utilize a strategy of clustering or grouping multiple greenhouse operations together. This is a deliberate economic model. By clustering, they share heavy infrastructure costs like cold storage facilities, distribution hubs, and paved access roads, making mid-sized operations financially viable. One of the most brilliant innovations here is the compost heat system. Planners increasingly site these greenhouses next to municipal compost facilities. As the city's organic waste decomposes, it generates immense heat, reaching temperatures of 140 degrees Fahrenheit or 60 degrees Celsius. Instead of wasting that energy, it is captured in the greenhouses overnight. This simple loop reduces reliance on fossil fuels. Furthermore, these massive greenhouse roofs double as rainwater catchments, perfect for harvesting stormwater. Finally, we arrive at the rural orchards. We are no longer talking about plots measured in square feet, but in thousands of hectares, a landscape of industrial-scale monocultures. Here, in places like California's Central Valley, efficiency isn't just a goal, it's a survival requirement. Because labor is scarce and expensive, these farms rely on heavy mechanization. We see GPS-guided tractors that drive themselves with inch-perfect precision, and mechanical shakers that harvest an entire nut tree in seconds. This shift requires a different kind of workforce. Fewer manual pickers and more skilled technicians to maintain these complex machines. Once the harvest is in, the clock starts ticking. This is where the cold chain begins. Produce has to travel hundreds of kilometers to reach the city or export ports. To prevent spoilage during these long trips, fruit is rapidly cooled and loaded into refrigerated trucks that act as mobile fridges. This system feeds the world, but it comes with a heavy price tag. Reliance on diesel fuel, the stress on shrinking aquifers and stable water supplies, and a significant carbon footprint. All right, class, switch your hats from students to systems designers. We are entering the guided design jam. I want you to team up and select one specific zone mentioned in the lesson. You might choose the T6 Urban High-Rise, a downtown apartment complex wanting a rooftop garden, or the Peri-Urban School looking to transform, a vacant asphalt lot. If you chose the high-rise, your primary constraint is weight. You cannot haul tons of wet dirt up 20 stories. Will you use lightweight soil mixes or a hydroponic system? How will you handle high winds? Electricity bills? If you chose the school lot, your constraint is the pavement. You cannot dig down. Will you design wicking beds or container systems? How will you capture rainwater from the gym roof? Keep these design challenges in mind as we move forward and label your inputs: sun, water, labor, and outputs. Now that we've journeyed from the urban core to the rural heartland, let's test our understanding with a few key review questions. First, how would you define the urban, peri-urban, and rural zones specifically in the context of food systems? As you define them, consider how land cost and food miles change across this gradient and why they share that unique inverse relationship we discussed. Second, looking at sustainability through the lens of a systems designer, what are two major trade-offs we face when comparing a high-tech rooftop farm to a massive rural orchard? Third, let's get practical. If you were a regional planner tasked with growing spinach, strawberries, and almonds for your local market, how would you divide these crops across the three zones to achieve the highest possible efficiency? Let's see how your strategies align with the economic and biological realities of the gradient. For the definitions, urban zones are high-density cities, peri-urban zones are the city edges or fringe, and rural zones are the remote countryside. As we move away from the city, land cost decreases while food miles increase. The inverse relationship exists because cities have expensive land but offer immediate proximity to millions of consumers. On trade-offs, rooftop farms are masters of low transport needs but require high energy for technology and lighting. Conversely, rural orchards scale efficiently and use free sunlight. but they are often water-heavy and distant from the people they feed. The crop test. Spinach belongs in the urban zone because it grows fast and spoils quickly. It needs to be as close to the consumer as possible. Strawberries are perfect for the peri-urban zone, where they can benefit from controlled greenhouse conditions near the city edge. Almonds must go rural. They require massive acreage and specialized heavy machinery that simply won't fit in a city center. True sustainability is about placing the right crop in its proper spatial niche. Welcome to Lesson B. Our focus now shifts from the where of geography to the how of engineering and action. The title is Climate Smart Growing Spaces, and the urgent question we face is, how do we grow more with fewer resources? We aren't just looking at a future with less water and arable land. We are facing wilder weather patterns that threaten stability. To survive, we need a strategy called Climate Smart Agriculture or CSA. But this goes beyond just using less water. It requires us to close loops, turning waste into fertilizer and stormwater into irrigation. As we explore these examples, ask yourself, how are these farmers balancing the trade-offs we learned in Lesson A to design systems that are truly resilient? Let's see how different zones adapt technology to solve this problem. So, what exactly is climate smart agriculture, or CSA? It is not just a buzzword or a single technology. It is a holistic approach to managing landscapes, cropland, livestock, forests, and fisheries that addresses the interlinked challenges of food security and accelerating climate change. Think of CSA as a three-legged stool. If you remove one leg, the strategy collapses. CSA emphasizes three core goals. Goal 1, productivity. We must sustainably increase agricultural productivity and incomes. This isn't just about growing more food. It's about growing food better so that farmers can thrive economically without degrading their land. Goal 2, adaptation. We must build resilience to climate change. This means designing farms that can withstand extreme weather events like droughts, floods, and heat waves. Whether it's through drought-resistant crops or improved water management, the goal is stability in an unstable climate. Goal 3, mitigation. We must reduce and/or remove greenhouse gas emissions where possible. This involves practices that lower the carbon footprint of farming, such as sequestering carbon in the soil or reducing methane from livestock. When a farm integrates all three of these goals, enhancing food security, adapting to climate stress, and mitigating emissions, it isn't just sustainable, it is climate smart. Let's zoom in on a masterclass in efficiency. The urban closed-loop microfarm. In nature, there is no such thing as waste. Everything is food for something else. This system brings that logic into the city to solve two problems at once: waste disposal and food production. First, the input. It starts with coffee grounds. In a standard city, tons of this nutrient-rich material end up in landfills every day. Here, we intercept it. We use it as a sterile, energy-rich substrate for decomposers like oyster mushrooms. Second, the conversion. Once the mushrooms are harvested, the leftover material isn't trash. It is spent substrate, pre-digested organic matter that is perfect for worms. We feed it into a vermicompost system, where red wigglers transform it into a potent, nutrient-dense fertilizer. Third, the vessel. We use that fertilizer in wicking beds. Think of this system like a two-story plant home. Down at the bottom is the water reservoir. It's basically a storage tank. Up top is the soil zone, where the plants actually grow. You add water through a fill pipe, and it sits in the reservoir. Then special wicking materials pull that water upward, kind of like a paper towel soaking up a spill. That keeps the soil evenly moist without you watering all the time. There's also an overflow pipe, which is like a safety drain, so it doesn't flood. And you can add extra layers, like a little sand barrier or mulch, to help manage water even better. Want to make it more closed loop? You can add a worm compost bin so nutrients cycle right back into the soil. Mulch and wood chips help hold moisture and improve soil over time. And interface mats or a false bottom keep the layers separate, so nothing gets clogged. This sip, don't gulp method eliminates runoff and evaporation, cutting water use by 40% while producing high-quality greens right in the neighborhood. This linked YouTube video looks at small-scale urban agriculture. It's all about research and development focused on creating semi-closed loop systems, where organic waste is turned back into food. In the video linked here, you'll see how black soldier fly larvae, fish, hydroponics, and organic farming can work together as one integrated system. The goal is to produce fresh food efficiently while using less water and reducing waste along the way. For those of you interested in high-tech engineering, Let's explore controlled environment agriculture, or CEA. We can actually integrate composting systems directly inside a high-tech greenhouse or vertical farm to create a biological engine for the entire facility. Typically, these vertical farms are expensive to run because they have to purchase liquid CO2 to boost plant growth and use massive amounts of electricity for heating. In this conceptual framework, we replace those external costs with internal biology by recycling city food waste into usable resources. By composting urban food waste and crop residues right on site, we trigger a natural decomposition reaction that releases two critical resources: thermal heat and carbon dioxide. In a fully closed loop, we capture that CO2 and pipe it directly to the crop canopy to fuel photosynthesis, while simultaneously using heat exchangers to capture the compost's warmth, which often reaches 60 degrees Celsius, to heat the greenhouse. This turns what was once considered urban waste into a vital resource for circular farming. Beyond energy and gases, this system allows for nutrient looping. This process diverts our reliance on synthetic fertilizers by cycling nutrients from the compost back into the crops. For example, essential elements like nitrogen, phosphorus, and potassium are reabsorbed through bioponic or soil systems. By closing this loop, we make city farming significantly more efficient and sustainable, especially as urban populations continue to grow. Let's look closer at the CO2 capture side of the loop. The carbon dioxide released as a byproduct of composting is used to speed up photosynthesis and boost plant growth. Crucially, this prevents CO2 from venting into the atmosphere, effectively closing the carbon loop. This highlights why these systems are so powerful. They cut food miles and chemical inputs while reducing our reliance on long, vulnerable supply chains. To make this work in a city environment, we need specific supporting technologies. These include biofilters to ensure high air quality and energy recovery systems like compost heat exchangers. We also utilize ozonation or UV treatment for pathogen control to ensure the system is safe for food production. While these technologies add complexity, they are necessary to manage the biological reactions safely within a built-up urban area. While the concept of biological engines is exciting, we have to address some risks, starting with the gas management challenges. Composting naturally releases CO2, but it also produces methane and ammonia as byproducts. If these gases are left unmanaged, they don't just threaten the plants, they contribute to air pollution and the greenhouse effect. To solve this, we must integrate scrubbers and biofilters into our design to ensure these gases are neutralized or captured before they can impact the surrounding urban environment. The second major risk factor is pathogens and food safety. If the composting process is improper or incomplete, it can leave behind harmful microbes that pose a risk of contaminating the very crops we are trying to grow. In an urban CEA setting, we cannot rely on luck. We must use active heat treatments, ozonation, or UV sterilization to guarantee that the system remains sterile and safe for public consumption. Finally, we have to consider the system trade-offs. Designing a closed-loop system is a balancing act between the energy we recover from compost heat and the physical space and financial costs required to build it. Additionally, biological systems can be unpredictable. Ensuring a stable, consistent release of nutrients from compost is much harder than using synthetic fertilizers. As designers, our goal is to navigate these uncertainties to create a stable, predictable, and resilient loop. When we bring large-scale composting into the heart of a city, we move from biology into the world of policy. Cities have very strict air quality regulations, and our systems must be designed to meet odor and pollution standards to remain compliant. Beyond the law, there is the issue of public perception. We have to build community trust. If neighbors associate these farm sites with smells or pests, they will resist them. Our engineering must be so precise that the public sees these not as compost sites, but as clean, green community assets. A climate-smart system is only successful if it is equitable. We have the opportunity to design these compost loops specifically to benefit underserved neighborhoods, turning local waste into local food. However, as designers, we must constantly balance the drive for high-tech efficiency with the need for community inclusion. We also have to navigate planning constraints, like restrictive zoning rules and difficult transport logistics, that can make it hard to scale these projects in the areas that need them most. So, why go through all this trouble? Because this is the definition of circular farming. By turning urban waste into resources, we drastically cut food miles and reduce our reliance on chemical fertilizers. This makes our city food systems far more resilient to the supply chain disruptions that often threaten long-distance logistics. As the global urban population continues to explode, making city farming more self-sufficient isn't just an innovation. It's a necessity. We've looked at the pieces of the puzzle: nutrient cycling, CO2 capture, heat recovery, and the very real challenges of pathogens and public trust. Now, the question is, how do we put these pieces together into a working, equitable system? This is where the Food Justice Planner comes in. It requires us to move from theory to action, coordinating garden tasks with policy changes and community outreach to ensure our food systems are as fair as they are efficient. Now, I want you to step into the role of the lead engineer. In this activity, you aren't just observing a system, you are troubleshooting it. Look closely at the process diagram on the screen. Your goal is to identify the failure points and intervene to optimize the chemistry. First, look at the aeration. If that compost pile sits stagnant, the oxygen levels drop, and the bacteria switch to anaerobic respiration. Suddenly, you aren't producing helpful CO2. You're pumping out methane, a greenhouse gas nearly 30 times more potent than carbon dioxide. Where would you install forced air fans or turning augers to keep the system aerobic and safe? Next, trace the energy flow. That active pile is generating temperatures up to 140 degrees Fahrenheit. If you let that escape, it's a waste. But if you capture it, it's free heating. Where would you place a hydronic heat exchanger to transfer that thermal energy into your greenhouse's root zone? Finally, consider the biofilter. Before any gas reaches your delicate crops, it must be scrubbed of ammonia and volatile organic compounds. Where is the most critical checkpoint for that filter? Remember, every intervention you sketch on this diagram shifts the inputs and outputs. You are designing the difference between a farm that pollutes and a farm that regenerates. Moving outward to the urban fringe, we encounter a brilliant infrastructure hack: compost-heated hoop houses. In this peri-urban zone, we finally have enough space to partner directly with large-scale municipal compost facilities. Here is the engineering magic. A rapidly decomposing compost pile is effectively a biological furnace, naturally reaching internal temperatures of 140 to 150 degrees Fahrenheit or 60 to 65 degrees Celsius. Instead of letting that thermal energy drift away into the atmosphere, farmers install hydronic loops, coils of water pipes buried deep inside the active compost mounds. As water cycles through the pile, it absorbs that free heat and carries it into the adjacent greenhouse to keep crops warm during cold nights. This simple innovation can cut the reliance on propane or electric heating by over 20%, effectively turning a waste processing site into a renewable energy hub. Furthermore, the massive surface area of these greenhouse roofs serves a dual purpose as a catchment system, harvesting stormwater to irrigate the very crops the compost is heating. Now, let's travel out to the true frontier: rural dryland farming, which covers 40% of the Earth's land surface. These are vast regions receiving less than 750 millimeters of rain a year, where water is the ultimate currency. The strategy here isn't just efficiency, it's autonomy. Here, farmers are ditching the diesel engine for wind power. By installing small-scale turbines, they can power groundwater pumps directly. This cuts the cord to the expensive and often unreliable electrical grid, allowing them to lift water from aquifers using the steady rural breeze. But pumping water is only half the battle. You have to keep it in the soil. That's where pulse drip irrigation comes in. Instead of flooding the field for hours, which leads to massive evaporation losses, these systems fire short, precise bursts of water directly to the root zone. It's like feeding a baby with a spoon instead of a fire hose. Finally, they treat the soil itself as a reservoir by adding biochar. This charcoal-like amendment acts like a sponge, physically locking moisture into the sandy earth so it doesn't drain away. By combining wind energy, precision pulses, and soil engineering, these farmers are proving you can grow food in the desert without draining it dry. Innovation in agriculture is never static. It is constantly migrating across the landscape. We are currently witnessing a fascinating cross-pollination of technologies across the entire urban-rural gradient. A perfect example of this is the nutrient film technique, or NFT, where plants are grown in a shallow, recirculating stream of water. While this technology was originally perfected for space-constrained urban rooftops to reduce water use by 40%, it is now migrating to the peri-urban fringe. Developers are utilizing the vast, flat roofs of warehouses to scale up production without paving over existing soil, showing how urban to peri-urban community gardens are evolving into larger regional systems. Similarly, we see rural hoop house techniques moving closer to the city edge for tomato production, while peri-urban packing house villages are being established further out in rural areas to support remote growers. When we move past the geography and analyze the hard data, the trade-offs between these systems become very clear. Urban NFT systems currently lead the way in water conservation, producing lettuce with only about 25 liters per kilogram, a mere fraction of the water required by traditional field farming. However, we must acknowledge that this comes with high energy costs for constant pumping and lighting. In contrast, peri-urban greenhouses find their efficiency by leveraging natural sunlight and compost-generated heat, which allows them to keep their energy footprint remarkably low, often staying under 10 kilowatt hours per kilogram of berries. Finally, out in the rural orchards where elements are harshest, the focus shifts to crop per drop. By integrating heat-resistant varieties with biochar soil amendments, these large-scale farms are pushing productivity to zero point 0.6 kilograms of citrus fruit for every single liter of water used. Now, let's train your eyes to see the invisible connections of a circular system, starting in the urban zone with a rooftop sack garden. This system is a masterclass in recycling found resources directly where people live. The loop begins with household food scraps, which are processed in an on-site compost bin to create nutrient-rich compost and leachate. Instead of relying on municipal water, the system captures both household rooftop rainwater and the often overlooked condensate from air conditioning units and appliances. These elements flow into a vertical sack garden, allowing residents to grow fresh food with zero food miles and no need for outside trucks or industrial help. As we move to the peri-urban zone, the loops scale up to bridge the gap between city waste and regional production. This system centers around a municipal compost pile that receives city food waste. We capture two critical outputs from this pile. First, heat ducts draw thermal energy from the decomposition process to warm hoop houses. Second, the nutrient-rich leachate and compost fines are used to nourish berry tunnels. This is paired with a storm water reservoir for irrigation. Additionally, woody waste can undergo pyrolysis in a biochar plant to create soil enrichments, forming a nearly closed loop cycle of nutrients, water, and heat. Finally, in the rural zone, our loops focus on resource autonomy and precision management over vast distances. Because these farms are often off-grid, a wind turbine provides the renewable energy needed to power groundwater pumps. The water is delivered through precision pulse drip lines to citrus trees, with the entire system monitored by soil moisture probes that send real-time data to a cloud dashboard. To close the loop on site, pruned wood from the trees is processed in a biochar kiln. This biochar is then returned to the orchard as a soil amendment, physically boosting the ground's ability to retain moisture and significantly reducing the amount of water needed for future seasons. Beyond the engineering and resource loops, we must consider the human element, the social impacts of these systems. Each zone offers unique benefits to the communities they serve. In the urban core, these systems bring fresh produce to food deserts faster, engage youth in hands-on learning, and help mitigate the urban heat island effect through city greening. In the peri-urban zone, these clusters create living wage jobs close to the city, provide a system for turning local food waste into valuable compost, and support small growers by maintaining shorter, more resilient supply chains. In the rural heartland, these large-scale farms are the engines of our bulk food supply and critical export revenue. While they rely on heavy mechanization, they remain the foundation of global food security. However, a truly climate-smart design must also account for the challenges and equity risks inherent in each zone. Urban challenges. High startup costs often limit the spread of rooftop farms to wealthier areas. There is also a risk of green gentrification, where these new amenities can inadvertently drive up rents and displace the very residents they were meant to serve. Peri-urban risks. As cities expand, land speculation can price out existing farmers. Furthermore, gaps in infrastructure, like poor roads or a lack of cold storage, can hurt smallholders trying to reach the urban market. Rural realities. Out in the heartland, the seasonal and migrant workforce often faces low wages and limited access to social services. Additionally, the long distances food must travel to reach consumers increase both the carbon footprint and price volatility. Now it's your turn to apply these concepts to your own environment. For this group design activity, your task is to create a pitch for a climate-smart strategy tailored for a school setting. Imagine you are designing a system that uses cafeteria food waste and captures rooftop runoff to grow leafy greens specifically for school lunches. You will need to decide which zone strategy, urban, peri-urban, or rural, is best suited for your specific school's location. As you build your plan, think about how you will close the loop between the waste coming out of the cafeteria and the fresh food going back into it. Before we move into the final lesson on metrics, let's review the core pillars of climate-smart agriculture we've covered. First, what are the three main goals of climate-smart agriculture, and how do they work together like a three-legged stool? Second, beyond the environmental data, what are some of the social benefits of these systems, such as job creation or food access, across the different regions? Third, thinking back to our urban engineering discussion, what are the primary challenges that limit our ability to scale up rooftop farms across an entire city? Let's see how your answers compare to the industry standards. The goals. The primary aim is to produce more food with fewer resources, that is, productivity, while simultaneously adapting to climate change, that is, resilience, and reducing greenhouse gas emissions from farming, that is, mitigation. Social benefits. These systems are powerful community tools. They create local living wage jobs, bring fresh produce to underserved food deserts, reduce the urban heat island effect, and support small growers through shorter, more resilient supply chains. Scaling challenges. While innovative, rooftop urban farms face significant hurdles, including high initial startup costs, limited physical access to suitable roofs, and the complex social pressure of green gentrification that can drive up local rents. Welcome to the final stretch. Lesson C. Tech and metrics that matter. Up until now, we've looked at beautiful designs and clever systems, vertical farms, circular loops, and smart tractors. But design is only half the story. The other half is proof. In the world of sustainability, marketing can be deceptive. A farm might look green because it's on a rooftop or uses hydroponics, but appearances can lie. If that rooftop farm burns more coal to power its lights than a tractor burns diesel to plow a field, is it actually sustainable? To answer that, we have to strip away the buzzwords and look at the complicated math. In this lesson, we are going to learn the language of efficiency. Input versus output. We will move beyond vague promises and start calculating real metrics. Specifically water use efficiency, that is, how many liters per kilo of food, and energy use efficiency, that is, how much electricity per kilo of food. By the end of this lesson, you won't just think a system is better. You'll be able to prove it. Why do we obsess over these metrics? It is not just for the sake of math. Metrics are the only tool we have to see the invisible. First, metrics guide investment. In the real world, we have limited capital, limited water, and limited land. We cannot afford to guess. Metrics serve as a roadmap, allowing us to identify exactly which systems yield the best results so we can make informed decisions about where to put our resources. Second, they reveal true efficiency. A vertical farm might look futuristic and green, but if the data shows it burns coal to run lights 24/7, the green aesthetic is just a disguise. Tracking the right data tells us how well or poorly a system is actually performing, cutting through the marketing hype. Finally, metrics allow us to compare apples to apples, or in our case, rooftop lettuce to rural lettuce. How do you compare a high-tech skyscraper to a dirt field? You need a common denominator. By standardizing our units, we gain the accountability required to distinguish between genuine sustainability and expensive experiments. Let's dive into our first critical metric: water use efficiency, specifically measured as liters per kilogram. This number cuts through the noise and tells us exactly how much blue water, our precious freshwater resources, it costs to produce 1 unit of food. In traditional soil farming, lettuce can be incredibly thirsty, requiring roughly 100 liters of water to grow a single kilogram. Why so high? Because in an open field, much of that water evaporates into the air or drains deep into the subsoil where roots cannot reach it. Now, compare that to a closed-loop hydroponic system. Here, we recirculate the water, capturing and reusing every single drop the plant doesn't drink. This drives the water cost down to about 25 liters per kilogram, a massive 75% savings compared to the field. But here is the catch, and it's a big one. In the field, gravity moves water for free. In a vertical hydro tower, you have to run electric pumps 24/7 to fight gravity. So, while you are saving water, you are spending energy. This illustrates the central tension of sustainable design. You rarely solve a resource problem without creating a new cost elsewhere. Now, let's shift our focus to the second pillar of farm efficiency: energy. In a vertical farm or shipping container, we aren't using free sunlight. We are paying for every photon. This brings us to the metric of biomass per kilowatt hour, or kWh. In stacked vertical systems, we face a challenge called the light decay curve. Because the layers are packed so tightly, we have to use more LEDs to ensure the middle and bottom tiers get enough light to grow. This significantly increases the energy used per unit of biomass produced. Compare this to field crops, where the energy input for light is zero, but the yield is entirely dependent on the whims of the weather. To understand how we optimize this metric, Let's look at a case study of container citrus. By using a controlled environment combined with biochar-enriched soil, growers can maximize their biomass while minimizing waste. In this system, sensors adjust the drip irrigation every 15 minutes based on real-time data, ensuring the plants are never stressed. This precision doesn't just save water, it boosts the biomass per kWh because the energy used to run the fans, pumps, and sensors is directly translated into fruit growth rather than keeping a dying plant alive. It proves that even in a high-tech container, we can reach incredible efficiency if we manage the inputs with enough precision. So, we reach the ultimate question. Which system is actually better? Is it the high-tech hydroponic tower that saves 90% of the water, or the traditional field farm that uses zero electricity for lighting? The honest answer is, there is no perfect solution. Sustainability is not a fixed target. It is entirely dependent on your location. Let's look at the constraints. If you are farming in a desert like Arizona, where water is liquid gold but sunlight is abundant and free, the smart choice changes. Here, you might choose a solar-powered hydroponic system. You accept the high energy cost because you can offset it with solar panels, and the water savings are worth every penny. Conversely, if you are in a rainy, temperate region like the Pacific Northwest where electricity is expensive but rain falls for free, a vertical farm makes little sense. Here, the smart choice is traditional soil farming, letting nature do the work. The best design is never about the gadgetry. It is about choosing the system that fits the specific local constraints of the land. This leads us to a humble but critical conclusion. In the complex world of agri-systems, perfect does not exist. Instead, we must rigorously define what better means for each specific context. Better is entirely subjective because it depends on your prioritized constraints. If your absolute priority is food security, generating the maximum amount of calories to prevent hunger in a growing population, then the industrial rural model, with its massive scale and mechanization, might be the better choice, despite its heavy reliance on fossil fuels. If your priority is resource conservation in a region facing extreme water scarcity, then a high-tech hydroponic system is better because it saves every drop, even if it demands a higher energy budget. If your goal is social resilience, rebuilding a community fabric, and providing local green jobs, then a labor-intensive urban rooftop garden is better, even if its total tonnage is small compared to a rural field. We use metrics not to find a single magic bullet, but to make our trade-offs transparent. Your job as a designer is to look at the data and say, I am choosing to spend energy here to save water there, and to explain why that compromise serves your community best. Now, we are going to move from theory to practice with the Water Ledger Challenge. In this upcoming lab, you will act as agricultural auditors. We are going to test two systems side by side. A hydroponic setup representing a high-tech urban farm, and a soil compost pot representing a peri-urban plot. Your job is to track every single drop. You will measure the exact volume of water you pour in versus the runoff that drains out. But we aren't just looking at water. We are looking at growth. You will record plant height, leaf count, and ultimately, fresh biomass weight. By the end of the week, you will calculate the water use efficiency or WUE for each system. The formula is simple but powerful. Milliliters of water consumed divided by grams of biomass produced. Will the hydroponic lettuce justify its complexity with massive water savings? Or will the soil system surprise you? You will use this real data to make a final design recommendation. If you had limited water, which system would you bet your harvest on? For those who want to test their system's thinking, let's step into the 1 acre challenge. Imagine you have inherited exactly 1 acre of land on the urban edge. But there is a catch. You have a strict resource wallet, you have a fixed budget for water and a budget for energy. You must now shop for your infrastructure. Do you spend your energy budget on high-tech hydroponic racks to maximize yield in a small footprint? Or do you spend it on solar panels to run efficient drip irrigation for soil crops? Every component you choose, from moisture sensors to LED lights, has a price tag in water and energy. Your task is to assemble a system that stays within budget while maximizing food output. Once you have your design, you will calculate your predicted water use efficiency and energy use efficiency. Then you have to defend it. Why did you prioritize water savings over energy? Why is your design the climate-smart choice for this specific plot? This isn't just math. It's strategic planning. Let's drill down into the specific math of the vertical stack. It isn't as simple as just stacking shelves like books in a library. It is a complex geometry problem with biological consequences. We are fighting a principle of physics called the inverse square law. This dictates that light intensity doesn't just fade. It drops off exponentially as you move away from the source. If you rely on massive ceiling lights, the top tier receives 100% of the energy, while the third tier down might receive only 15%. You end up with a Goldilocks failure. The top plants scorch while the bottom plants starve. To solve this, we cannot rely on ambient lighting. Instead, we must engineer every single shelf as an independent ecosystem with its own dedicated LED strip. This guarantees that every leaf receives the exact number of photons it needs to conduct photosynthesis. However, this creates a new challenge: heat. Every watt of light adds thermal energy that must be cooled. Therefore, efficient design becomes a math equation. Finding the exact spacing that maximizes your biomass per kilowatt hour ratio without wasting a single photon. Let's ground our metrics in a high-stakes, real-world example: the Vitalochus lab at UCR. They are tackling the citrus industry's greatest threat, Huanglongbing or HLB, an incurable bacterial disease spread by a tiny insect vector, the Asian citrus psyllid. In traditional open orchards, this disease is decimating groves. The lab's strategy is a masterclass in environmental exclusion. Instead of spraying more chemicals, they moved the orchard entirely indoors under specialized high-density screenhouses. This physical barrier disrupts the disease triangle by permanently separating the host tree from the insect vector, ensuring the trees remain infection-free. But they didn't stop at defense. They optimized for efficiency. The trees are grown in pots using a soil mix amended with biochar, a carbon-rich sponge that drastically increases water retention. Coupled with real-time soil moisture sensors, the irrigation system operates on a demand loop, watering only when the plant transpires. The result? A 90% reduction in water use compared to field-grown trees and zero nutrient runoff. They have effectively turned a thirsty, vulnerable crop into a secure, water-sipping asset. Before we wrap up our final lesson, let's review why data is the most important tool in a climate-smart designer's toolkit. Marketing can be misleading, but the math doesn't lie. As you look at the review questions on this slide, think about the quantitative side of sustainability. First, why do we specifically need metrics like liters per kilogram or biomass per kilowatt hour when we are designing these farming systems? Second, we've discussed how hydroponic tower lettuce systems are masters of water conservation. But what is the hidden trade-off of that efficiency, and how does that change your overall design? Third, finally, if you were asked to check a farm's actual efficiency right now, what are the two key metrics you would look for to prove its sustainability? Here are the answers to the review questions. Why do metrics matter? These numbers reveal exactly how much water or energy is required to grow a crop. They strip away greenwashing and allow us to compare different systems fairly, ensuring we make the smartest investment and design decisions for a specific location. The hydroponic trade-off. While a hydroponic tower uses significantly less water than soil-based farming, it often requires much more energy. This electricity is needed to power LED lights, circulation pumps, and complex temperature control systems. A balanced design must weigh these costs against the water savings. The efficiency check. The two gold standard metrics for farm efficiency are water use efficiency, that is, liters used per kg of yield, and energy use efficiency, that is, kWh energy used per kg of yield. Together, these show how sustainable a growing system really is. As we conclude Module 6, let's solidify the three pillars that will define your approach to agricultural design. We aren't just memorizing facts. We are building a new mental model for resilience. First, the gradient is a continuum, not a binary. We must dismantle the old city versus farm divide. Instead, view the landscape as a collaborative spectrum. Urban systems are our social engines, excelling at education and community integration, while rural systems remain our calorie engines, doing the heavy lifting for global food security. A truly resilient future relies on optimizing the connection between these zones rather than choosing one over the other. Second, remember the energy water seesaw. We discovered that efficiency is often a trade-off. When you act as a water ninja in a vertical farm, recycling 98% of your moisture, you pay a steep price in electricity to run pumps and lights. Conversely, field farming is energy efficient thanks to the sun, but expensive in water use. You cannot cheat physics. You can only choose which resource you are willing to spend based on what is abundant in your region. Finally, prioritize context over technology. The most advanced farm isn't the one with the most sensors. It is the one most attuned to its environment. Whether you are excluding vectors in a citrus grove or capturing rainwater on a rooftop, The perfect design is simply the one that best navigates your local constraints. Don't look for a silver bullet. Look for the right tool for the job. Let's visualize our entire journey on one single canvas. The Module 6 Mind Map. At the center, we anchor our core theme, climate-smart agriculture. Branching outward, we see our three distinct zones: urban, peri-urban, and rural, not as competitors, but as connected organs in a single body. Follow the urban branch and you hit the trade-off node: high energy costs exchanged for massive water savings. Follow the rural branch and you find scalability and soil carbon, efficiently producing calories but demanding strict water management. The most important lines on this map are the connectors. Notice how the waste from the urban branch loops back to feed the peri-urban soil? That is the circular economy in action. This visual summary simplifies the complex data we've analyzed. Whenever you get lost in the details of kilowatt hours or nutrient ratios, return to this map to see where your specific design fits into the larger, living ecosystem. This web of connections represents the future of our food system. This isn't just academic theory. We are looking at a rapidly exploding job market. The future of farming isn't just about driving a tractor anymore. It's about systems thinking. If you thrive in the urban zone, consider a career as a green infrastructure designer or urban policy planner. You would be the one writing the smart codes we discussed or engineering the load-bearing structures for rooftop farms. If you love robotics and controlled environments, the peri-urban zone needs greenhouse systems engineers. You would be designing the automation that runs the climate control, lighting, and nutrient delivery systems in high-tech glasshouses. And for those who love big data and open horizons, the rural zone offers careers as precision ag technicians and drone data analysts. You would be using satellite imagery and soil sensors to optimize water use across thousands of acres. The agriculture of tomorrow needs coders, biologists, and engineers just as much as it needs growers. Next up, you get to do the science. We are moving from theory to practice with two interconnected hands-on investigations that force you to think like systems planners. First, in the Light Bio Lab, you will test how specific variables drive plant growth. You will compare different light spectra, blue, red, or a full spectrum mix, with two distinct growing media: a high-tech urban hydroponic system and a peri-urban soil and compost mix. You won't just watch the lettuce grow. You will measure the system's pulse. You will track plant height, leaf number, and, crucially, every drop of water added versus the runoff collected. This data will feed into your second activity, the water budget ledger, where you will calculate the actual water use efficiency in milliliters per centimeter of growth. This reveals the invisible trade-offs: how a choice about LED color or soil type ripples through the system, affecting resilience and resource costs. We need evidence-based decisions, not guesses, so get ready to get your hands dirty and your calculators out. We've traveled from the balcony to the back 40. We've seen that there is no perfect farm, only the right farm for the right place. Urban farms connect us. They turn food deserts into hubs of engagement. Peri-urban farms protect us. They act as the green buffers for our cities. Rural farms feed us. They provide the calories a hungry planet demands. But existence alone is not enough. The future demands that we move beyond linear consumption, where food ends up in a landfill, to a proper circular system. We need nutrient-rich city waste returned to the country's soil, linking these zones into a resilient loop capable of withstanding climate shocks. That is the grand challenge of the urban-rural gradient, not just to grow food, but to heal the cycle. You now have the tools to solve it. Good luck with your designs.